Right now, at this exact second, you are not living inside a living galaxy. You are living inside a corpse. The Milky Way already died once, billions of years ago, and everything you see in the night sky, every star, every planet, every atom in your body, is built from the ruins of that death. In this space documentary, we step into the ghost of our own galaxy, and what we find will reshape everything you thought you knew about where you come from. We'll show you the scientific evidence of when it happened. We'll reveal what actually killed it, and what brought it back. And at the end, we'll answer the question no one wants to ask: is it going to die again? And I know how that sounds. Believe me, when I first came across this research, I almost didn't believe it either. I went back to the papers 3 times. 4 times. Because the claim feels too large. Too personal. The idea that the home galaxy we were born into is not a thriving, living system, but something operating on borrowed time, running on fumes and ancient infrastructure, that's not a comfortable idea to sit with. But the data doesn't care about our comfort. So let's go. Before we can understand the death, we have to understand what was alive. Because the early Milky Way was not the elegant, sweeping spiral we picture when we close our eyes and imagine our galaxy. It was something almost unrecognizable, violent, chaotic, and burning with a kind of intensity that the modern galaxy cannot come close to matching. The Milky Way formed approximately 13.6 billion years ago. Put that in context, the Big Bang happened 13.8 billion years ago. Our galaxy is almost as old as the universe itself. When it began assembling from collapsing gas and dark matter, the cosmos was barely 200 million years old, a toddler by any measure. And the galaxy that emerged from that infancy was nothing like the place our sun calls home. The very first stars, astronomers call them population 3 stars, were extraordinary objects. We've never seen one directly, because they're all gone now. But from the physics of what the early universe contained, we can reconstruct what they must have been. Enormous. Some of them reaching estimated masses of 300 to 400 times the mass of our sun. These were not stars in any intuitive sense. They were nuclear furnaces so intense, burning so hot, that they would have outshone entire modern galaxies on their own. A single population 3 star would have been a beacon visible across the observable universe. And the galactic structure around them? There were no spiral arms. No calm, flat disk. No orderly rotation. The young Milky Way was a chaotic, irregular mass, more like a violent storm of star formation than the stately structure we inhabit today. Star formation was happening at a rate 10 to 20 times higher than anything we measure in our galaxy today. The Milky Way was overproducing stars at an almost reckless pace, burning through its fuel with the extravagance of something that doesn't know it has a budget. What would a night sky look like if you stood on any hypothetical planet in those first few billion years? The word blazing doesn't do it justice. Star density was dramatically higher. Nearby supernovae would have been visible regularly, not once in a generation events, but almost routine features of the sky. The galactic environment was, by our standards, terrifyingly alive. Dark matter was already doing its invisible work, the scaffold that held the chaos together, the gravitational skeleton around which everything was assembling. And even in this early period, the Milky Way was already a predator. Neighboring proto-galaxies were being gravitationally captured, stripped, absorbed. Our galaxy was consuming smaller structures from almost the moment it formed. The violence was not accidental. It was structural. You know what gets me about this? Every element heavier than hydrogen in your body, the iron in your blood, the calcium in your bones, the carbon in every molecule of your DNA, it was forged inside one of these ancient, dead population tree stars. When they exploded, and they all exploded, because nothing that large survives for long, they scattered those newly created elements across the proto-galaxy. You are made of the first generation of stars that ever lived. That's not poetry. That's chemistry. But here's the problem with burning that bright: you burn through your fuel. And what happens to a system that burns faster than it can replenish? It hits a wall. And the Milky Way, approximately 10 to 11 billion years ago, hit its wall. Scientists call it the cosmic noon, the moment our galaxy reached its peak, and then something catastrophic pulled the emergency brake. But what actually stopped it? Approximately 10 billion years ago, the universe hit cosmic noon. This is the technical term astronomers use for the epoch when star formation across all galaxies simultaneously reached its absolute peak. Across the entire observable universe, galaxies were producing stars at a rate roughly 50 times higher than today. The cosmos was at its most productive, most intense, most alive, and then it started sliding down the other side of that peak, and it has never stopped sliding. The Milky Way's star formation rate today sits at roughly 1 to 2 solar masses of new stars per year. At cosmic noon, estimates suggest it was forming somewhere between 10 and 20 solar masses per year. Do the arithmetic: our galaxy is currently operating at perhaps 5 to 10% of its former capacity. The engine is still running, but it's barely idling compared to what it once was. What makes this concrete rather than abstract is the data from the Gaia Space Observatory. Gaia is a European Space Agency mission that has been mapping the positions, movements, and ages of over 1 billion stars in the Milky Way with extraordinary precision. When researchers analyzed Gaia's data on the age distribution of stars, where the young ones are, where the old ones cluster, what they found was not a gradual decline. It was a cliff. A sharp, dramatic drop-off in star formation that began approximately 8 to 10 billion years ago and has continued, with occasional interruptions, ever since. I was going through the data visualizations from that research while putting this together, and there's one graph that shows the star formation rate over time, and it looks exactly like what I just said: not a slope, not a curve. A cliff. I sat with that image for a long time. The technical name for what's happening is stellar quenching. That's when a galaxy stops, or dramatically reduces, its production of new stars. And the mechanism behind it involves something almost counterintuitive: the galaxy starts to sabotage itself. Stars form. The most massive ones live fast and die violently as supernovae. Those explosions send shock waves through the surrounding gas clouds, the very material needed to form more stars. The shock waves heat the gas, disperse it, make it unavailable for further star formation. The galaxy, in a sense, is burning the table it's sitting at. This connects directly to why cosmic noon matters for the history of our planet, even though Earth didn't exist yet. The type of stars that form in the post-noon era are different from what came before. Lower mass, longer-lived, more chemically enriched. The slowdown directly determines what planetary systems become possible. The fact that our Sun exists, that Earth formed with the right chemical composition to support liquid water and biology, all of that traces back to where the Milky Way was in its star formation history when our solar system condensed from a cloud of gas and dust 4.6 billion years ago. There's a parallel here that the creator in me finds almost irresistible. The Milky Way hit a midlife crisis, slowed down, started questioning its trajectory. But unlike most midlife crises, this one left measurable scars on the structure of an entire galaxy. And that brings us to the question at the heart of this documentary. Slow death and actual death are two different things. What does it actually mean for a galaxy to die? Because not everyone agrees the Milky Way even survived. There is a paper, published in one of the world's most respected astrophysics journals, that argues the Milky Way effectively died once already. And the key piece of evidence is hiding in the age of the stars above your head right now. Before we can say the Milky Way died, we need to agree on what galactic death actually means. And this is where the science becomes contested in ways that are genuinely interesting, not contested in the way that bad science gets contested, but in the way that frontier science always does, multiple serious researchers, looking at the same data, reaching conclusions that don't fully overlap. Astronomers use several competing definitions of galactic death. The first is star formation quenching. The galaxy simply stops producing new stars, essentially running out of raw material or the conditions to use it. The second is structural death. The galaxy's shape and internal dynamics change so fundamentally that it can no longer function as it once did. Spiral arms dissolve. The disk flattens or disperses. The third definition involves the central supermassive black hole. If the black hole ceases activity, the feedback mechanism that regulates the galaxy shuts down. And the fourth, the most final of all, is thermodynamic death. All stellar processes wind down, the last stars burn out, and what remains is a cooling graveyard of dark remnants. Each of these definitions places the Milky Way in a different position. And that's the uncomfortable part. In 2023, research published in Nature Astronomy proposed something with profound implications. Galaxies, the data showed, are not distributed across a spectrum of star-forming activity. They cluster into two distinct groups, either actively forming stars or effectively quenched. The transition between those two states is not a gradual fading. It is abrupt. It is, in the words of the researchers, catastrophic, like a switch being thrown rather than a dial being turned. And the Milky Way sits in between those two groups, in a classification zone that astronomers call the Green Valley. The name sounds pastoral. It isn't. Let me explain the color coding, because it matters. Young, massive stars burn hot and glow blue-white. Old, smaller stars glow red and cool. The color of a galaxy, its overall tint in telescope images, directly reflects what kinds of stars it contains, which reflects how actively it's forming new ones. Actively star-forming galaxies cluster in what astronomers call the blue cloud. Dead, quenched galaxies cluster in the red sequence. The Green Valley is the transition zone between them, and galaxies that enter it almost never return to full activity. It is, without being melodramatic about it, a one-way door. I want to stop here for a second because I realize the Green Valley sounds almost peaceful. Like a nice place to be. It's not. In galactic terms, the Green Valley is where galaxies go to slowly stop being galaxies. The hospice ward of the universe. And the Milky Way may already be checked in. Andromeda, our nearest large galactic neighbor, appears to have already passed through a period of quenching and is now in a secondary active phase, a brief revival before a longer decline. Some researchers argue the Milky Way went through the same pattern. That there was a first period of effective death, genuine quenching, followed by a partial recovery. Which means what we see when we look up at the night sky is not the Milky Way at its prime. It may be the Milky Way's second attempt. Its second wind. The galactic bar, the elongated central structure that runs through the core of our galaxy, plays a possible role in this. The bar acts as a funnel, channeling gas toward the galactic center, feeding the supermassive black hole at the core, which in turn generates outflows powerful enough to push star-forming gas out of the disk entirely. The galaxy contains the mechanism of its own suppression built into its structure. so we know what galactic death looks like. But the Milky Way's death wasn't just a slow fade. The evidence suggests something far more dramatic happened, something that sent shockwaves through the entire structure of our galaxy. And the weapon was our own black hole. Sagittarius A*, the supermassive black hole at the center of our galaxy, is almost completely silent today. But the scars on our galaxy suggest that once, not that long ago in cosmic terms, it wasn't silent at all. It was screaming. Sagittarius A* currently has a mass of approximately 4 million times the mass of our Sun. By the standards of supermassive black holes, it is unremarkable in size, and almost uniquely quiet in behavior. It accretes matter at an exceptionally low rate. It produces almost no jets, no powerful outflows, no X-ray flares of significance. For a black hole at the center of a major galaxy, it is nearly dormant. But nearly dormant is not the same as always dormant. And the evidence that it wasn't always this quiet is written in the structure of the galaxy itself, in two enormous structures that extend perpendicular to the galactic disk, looming above and below the plane of the Milky Way like the aftermath of a detonation. Because that is precisely what they are. The Fermi bubbles were discovered in 2010 using data from NASA's Fermi Gamma Ray Space Telescope. Two vast lobes of high-energy gas and radiation, each extending roughly 25,000 light-years above and below the galactic plane. To put that scale in perspective, if you were to draw the Milky Way's disk as a dinner plate, the Fermi bubbles would extend off the table on both sides, reaching down to the floor. These are not subtle features. These are the scars of something catastrophic. The estimated energy of the event that created them is approximately 10 to the power of 55 ergs, the equivalent of 100,000 supernovae detonating simultaneously. And the timeline? Approximately 6 to 9 million years ago. Not billions. Millions. In galactic time, that's recent. Startlingly recent. Here's the detail I find hardest to process. Our genus, Homo, was already walking the Earth 6 to 9 million years ago. Our early ancestors existed when the most recent Fermi bubble event was initiated. We were already here. Not watching the sky, not yet, not with anything like awareness or astronomy. But the light from that eruption, in gamma rays and X-rays, was washing over Earth while bipedal hominids walked African savannas. We were already here for the aftershock. Then, in 2020, an even larger structure was discovered. The Rosetta bubbles, detected by the German-Russian Rosetta Space Telescope, extend approximately 45,000 light-years from the galactic center, larger than the Fermi bubbles, and potentially from a separate, earlier eruption event. Two catastrophic outflow events, evidenced in the data. Two separate moments when Sagittarius A* was not quiet at all. The mechanism works like this: during an active galactic nucleus phase, what astronomers call an AGN phase, the black hole begins accreting material at a dramatically higher rate. That infalling matter heats to billions of degrees. The friction and magnetic processes involved generate jets and winds of relativistic particles. Those winds are powerful enough to sweep star-forming gas out of the galactic disk entirely, not slowly, not gently, but in a violent expulsion that clears the fuel supply the galaxy needs to form new stars. In a very literal sense, the black hole vomited the galaxy's own fuel out into the halo above and below the disk. The self-regulating galaxy theory frames black holes as thermostats. When star formation gets too high, the black hole activates, blows out gas, quenches star formation, and then goes dormant as the available fuel around it runs out. Slowly, over millions to billions of years, conditions recover. Gas cools and falls back in. And the cycle potentially repeats. The Milky Way may have gone through multiple such cycles, periods of activity, AGN eruption, quenching, recovery, activity again. What we call the galaxy's death may actually be one chapter in a longer pattern. But was the black hole's eruption the killing blow, or did something come from outside the Milky Way that delivered the real damage? Because the evidence of what we're going to look at next looks like a wound that came from the outside. Meet Gaia Enceladus. A galaxy the Milky Way murdered and consumed billions of years ago. And the collision that killed it may have also, temporarily, killed us. In 2018, the European Space Agency released a tranche of data from the Gaia Observatory that transformed galactic archaeology overnight. Hidden within the orbital characteristics and chemical signatures of stars in the Milky Way's halo, a research team led by Amina Helmi identified something extraordinary, a coherent population of stars that did not form in the Milky Way. They were born elsewhere. In another galaxy entirely. A galaxy that no longer exists because ours consumed it. That galaxy is now called Gaia Enceladus, or sometimes the Gaia sausage, the latter name coming from the elongated, sausage-like shape its stars trace in velocity space when you map their orbits. At the time of the collision, Gaia Enceladus had approximately 100 billion solar masses in stars, roughly a quarter of the Milky Way's stellar mass at that moment. This was not a minor accretion event. This was not the Milky Way quietly absorbing a small satellite. This was a collision between two substantial galaxies, and the consequences reshaped everything. The merger happened approximately 8 to 10 billion years ago, and the timing overlaps directly with the Milky Way's dramatic star formation slowdown. Whether the collision caused the slowdown, contributed to it, or simply coincided with it is something researchers are still working through. But the correlation is striking enough that it cannot be dismissed. I keep coming back to this image. There are stars in our sky tonight that were born in another galaxy. They formed around a different galactic center, in a completely different gravitational environment. And then that galaxy was destroyed, gravitationally torn apart, its stars stripped away and swallowed by ours, and those stars have been orbiting the Milky Way's core for billions of years ever since. They are refugees. Survivors of a civilization of stars that no longer has a home. And we orbit alongside them without knowing their names. The collision left fingerprints across the entire Milky Way that we're still reading today. The most obvious, the Milky Way's thick disk, that ancient, puffed-up layer of old stars that sits above and below the thin disk where our solar system lives, is believed to have been formed, at least in part, by the gravitational turbulence of the Gaia Enceladus merger. The thick disk is built from the ruins of a galaxy we absorbed. The very structure we live in is partly a graveyard. The gravitational chaos of two large galaxies merging would have been extraordinary. Shock waves propagating through the interstellar gas. Compression triggering bursts of star formation in some regions. Dispersal and heating disrupting star formation in others. The net result, a period of intense activity followed by a sharp crash, exactly the pattern that post-cosmic noon data shows. And Gaia Enceladus was not the only one. The Sagittarius dwarf galaxy is currently being shredded and absorbed, its stars strung out in streams that wrap around the Milky Way in long arcs, identifiable by their chemistry. The Sequoia galaxy, another dwarf, was absorbed at some point in the past. And Kraken, a merger estimated at roughly 11 billion years ago, may have been the most massive merger event in the Milky Way's history, older than Gaia Enceladus, leaving its own structural legacy in the galactic bulge. The Milky Way is a serial cannibal. It has consumed multiple other galaxies across its lifetime, incorporating their stars, their gas, their gravitational energy into its own structure. We are living in a galaxy that is partly built from the wreckage of others. The ghost of the Milky Way contains, within it, the ghosts of galaxies that died so ours could survive. So we have the picture now forming: an overactive youth, a catastrophic slowdown, a violent black hole eruption, and a galaxy-scale collision that restructured our entire home. But here's the twist the title is really reaching for: after all of that, did the Milky Way actually come back? Or is everything we see right now just the aftermath of something that never fully recovered? There's a concept in astrophysics called a zombie galaxy. A galaxy that looks alive, still has stars, still has structure, still has the semblance of function, but has fundamentally lost the ability to truly renew itself. And the data suggests the Milky Way fits that description more closely than any of us would find comfortable. The modern Milky Way, from any outside vantage point, would look like a galaxy. Two main spiral arms extending from a central bar, a thin disk of star-forming gas and dust, a halo of older stars above and below the plane. It would register in a galaxy survey as an active, star-forming spiral in the blue cloud, or near it. A living galaxy. But closer examination reveals something more troubling. The Milky Way currently forms approximately 1.65 solar masses of new stars per year. That number has been declining for billions of years, and there is no known mechanism driving it upward in a sustained way. We are on a slope, and the slope only goes in one direction. The raw material for star formation, primarily cold hydrogen gas in the interstellar medium, is being consumed faster than it is being replenished. Current estimates suggest that our cold gas reserves, at the current consumption rate, could sustain star formation for perhaps another 1 to 2 billion years before a significant further drop-off. In the context of a universe's age, that is not a long time. In the context of a human lifespan, it is of course incomprehensible, but the point is not whether it affects us personally. The point is what it says about where the Milky Way is in its life cycle. What Gaia data revealed about the age distribution of stars in our galaxy includes something genuinely unexpected: a burst of star formation roughly 2 to 3 billion years ago, possibly triggered by the ongoing absorption of the Sagittarius dwarf galaxy, followed by a return to decline. The Milky Way had a brief revival. It rallied. And then it continued declining. Like a patient who has a good week and the family dares to feel optimistic, and then the numbers go the wrong direction again. Andromeda shows an almost identical trajectory. It went through a period of quenching, had a secondary burst of activity, and is now in measurable decline. Both galaxies are following arcs toward mutual quenching, and their collision in approximately 4.5 billion years will trigger one final, dramatic wave of star formation before the merged system settles into permanent stellar silence. Researchers at the University of California, Riverside formally characterized zombie galaxies in 2021, systems that retain the structural appearance of living galaxies while showing metabolic indicators of death. Declining star formation rates. Depleting gas supplies. Aging stellar populations dominating the light output. The Milky Way scores positively on multiple criteria in that classification. What does this mean for the sky above our heads? The night sky we see is already predominantly old light. The bright blue-white stars that define the most recognizable constellations, Orion's belt, Sirius, Rigel, are young and short-lived on stellar timescales. They are the exceptions. The majority of stars in our galaxy are older, cooler, dimmer. And the ratio is moving in one direction. In 5 billion years, assuming anyone is still here to look up, the night sky will be dominated by red and orange stars, dimmer, less dramatic, a galaxy running on its aging infrastructure. Our Sun is itself a product of the decline. It formed approximately 4.6 billion years ago, during a period when the Milky Way was already well past its cosmic noon peak. We are children of a middle-aged galaxy. Our star was born when the galaxy had already begun its long slowdown. The Sun is not an artifact of the Milky Way's prime, it is an artifact of its descent. I want to be honest with you here, because this is where some science communicators soften the picture and say, well, the Sun has 5 billion years left, and that's true, and your grandchildren's grandchildren's grandchildren are going to be fine. All of that is true. But I think you came here for the real picture, not the comforting version. So here it is, we live in a galaxy that has already begun dying. Our Sun is a product of that dying galaxy. And the light you see in the night sky, you're looking at a ghost. But here's what makes this more than just a story about death. It's also a story about what death creates. Because the dying of the Milky Way's first generation didn't end in nothing. It ended in us. And that changes everything about how we think about our place in this ghost galaxy. There's a hypothesis gaining serious traction in the scientific community that says complex life could only have emerged in a galaxy at exactly this stage of its life cycle. Too early, and the chemistry isn't right. Too late, and the environment becomes hostile. The Milky Way's death may have been necessary for life to exist at all. This is the part of the story I've been building toward. And I'll be honest, I've read a lot of papers preparing for this section, and I don't think I've fully processed what it means. So let's go through it together. The universe began, as far as we can determine, with 3 elements: hydrogen, helium, and trace quantities of lithium. That was it. That was the entire periodic table in the first few minutes after the Big Bang. No carbon. No oxygen. No nitrogen. No iron. No calcium. No phosphorus. None of the elements that biology requires, that geology requires, that rocky planets require. A universe of only hydrogen and helium cannot produce life. It cannot produce Earth. It cannot produce anything we would recognize as complex chemistry. Everything else, every element heavier than lithium, had to be made. And the only mechanism the universe has for making heavy elements is stellar death. The population 3 stars, those enormous, violent first-generation furnaces we talked about at the beginning, fused hydrogen and helium into carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur. When they exhausted their fuel, they didn't just fade. Stars of that mass die as parent-stability supernovae, explosions so complete that virtually the entire star is converted to energy and scattered outward. The heavy elements those stars had spent millions of years manufacturing were distributed across the proto-galaxy in a single catastrophic moment. The galaxy was seeded with complexity through the death of its first generation. Second-generation stars formed from this enriched material. They built on what the first generation had scattered, manufacturing even heavier elements and distributing those in turn when they died. And then our Sun, a third-generation star, a population 1 star, formed from a gas cloud that had already been enriched by 2 complete cycles of stellar death. The Sun contains heavy elements. Earth contains heavy elements. You contain heavy elements. None of that was possible without the death of 2 prior generations of stars. You are not made of star stuff in any simple sense. You are the specific byproduct of a galaxy's death cycle, compounded across 2 complete generations of stellar birth and extinction. You are what happens when a galaxy digests itself across 13 billion years. The galactic habitable zone concept, first formalized by Lineweaver and collaborators in 2004 and refined multiple times since, makes this even more precise. Not all parts of the Milky Way are capable of supporting life as we know it. The galactic center, where star density is extreme and radiation from Sagittarius A* and neighboring stellar activity is intense, is almost certainly hostile to complex biology on long timescales. The outer regions of the galaxy lack the metallicity, the concentration of heavy elements, necessary to build rocky planets. Earth-like worlds essentially cannot form there. But between approximately 23,000 and 29,000 light-years from the galactic center, conditions are different. Star density is moderate. Radiation environment is manageable. Metallicity is high enough from billions of years of stellar death cycles to support rocky, differentiated planets with liquid water. Our solar system sits at approximately 26,000 light-years from the center. We are in the sweet spot. And that sweet spot only exists because the Milky Way went through the specific history it did, the violent early phase, the enrichment by dying stars, the cannibalism events that added to the chemical diversity of our galactic neighborhood. Complex multicellular life on Earth emerged approximately 600 million years ago. The universe is 13.8 billion years old. It took 13.2 billion years of stellar death, galactic evolution, merger events, black hole eruptions, and chemical enrichment to produce the conditions in which complex biology became possible. We are not early arrivals in cosmic history. We arrived at the moment we were supposed to, when the death cycle had finally produced enough chemical richness to support us. The timing argument for the Fermi paradox cuts directly through this. If complex life requires this specific stage of galactic chemical evolution, it powerfully constrains when in cosmic history advanced civilizations can emerge. We may be among the first in our galaxy to reach this level of complexity, not because we're exceptional, but because the galaxy needed this long to produce the right conditions. And the window in which those conditions exist, the window of high metallicity, manageable radiation, stable stellar environments, may be relatively narrow on cosmic timescales. The Milky Way didn't create life despite dying. It created life because it died. The death of galaxies is the metabolism of the universe. You are the ghost of the Milky Way, given consciousness and curiosity and the capacity to look back at the galaxy that made you and wonder what happened. I've said that out loud a few times now while preparing this section, and it still doesn't feel fully real. If the death of the Milky Way is what made life possible, then every extinction event that has threatened biology on Earth, every supernova that has bathed our solar system in radiation, every catastrophic galactic event in our past, all of it is part of the same alchemical process. The universe is not indifferent. It's not cruel. It's just alchemical. It converts death into complexity. And we are the complexity. So the Milky Way's decline is ongoing and measurable. But the next dramatic event, the Andromeda collision, is not going to be a simple death. It is going to be a transformation. And other forces, already in motion, will eventually bring our galaxy to its true and final ending. Here is the timeline. Andromeda, Messier 31, our nearest large galactic neighbor, is approaching at approximately 110 kilometers per second. In roughly 4.5 billion years, the gravitational interaction between the two galaxies will begin in earnest. The actual merger will play out over the following 2 to 3 billion years as the two galaxy cores spiral toward each other, merge, and settle into a new structure. The result is currently nicknamed Milkomeda or Milkdromeda, a large elliptical galaxy, no longer spiral, no longer with disk structure or spiral arms, formed from the combined stellar populations of both galaxies. During the collision itself, the sky, if anything with eyes exists to see it, will be spectacular beyond anything in our current experience. Two galactic cores visible simultaneously, the whole sky blazing with triggered star formation as gas clouds collide and compress, new star clusters igniting across the merged structure. It will be the last fireworks show the Milky Way ever puts on. The probability of our solar system being directly struck by another star during this event is vanishingly small. The distances between individual stars are so enormous that even when two full galaxies interpenetrate, direct stellar collisions are extraordinarily rare. But the Sun's orbit will be dramatically disrupted. The gravitational chaos of the merger could fling our solar system to a completely different location within the merged galaxy, or eject it into the intergalactic void. Earth may survive the merger while being relocated to somewhere that looks nothing like home. This is somewhat academic, because the Sun itself will have ended approximately 5 billion years from now, entering its red giant phase, expanding to engulf the inner planets, and eventually collapsing to a white dwarf. The Sun's death is a nearer event than the Andromeda merger's completion. We won't be here to see the final product either way. After Milkometa forms and star formation ceases, the remaining stars will continue burning for timescales of up to 100 trillion years. The last red dwarf stars, the most fuel-efficient, longest-lived stars in the universe, will finally flicker out on those enormous timescales. What remains will be white dwarfs slowly cooling to black dwarfs, neutron stars, and the black holes that remain from the merged galactic cores. Then, on timescales ranging from 10 to the power of 67 years to 10 to the power of 100 years, even black holes evaporate via Hawking radiation, a quantum process so slow it makes geological time feel urgent. The Milky Way's final death is not a bang. It's a whisper. The last Hawking radiation from what was once Sagittarius A * fading into an increasingly cold and empty universe. There's something I find almost comforting about the Andromeda merger, which I know is a strange reaction to have. But when I picture that future sky, two galaxy cores visible, star formation blazing back to life one last time, the universe putting on a final show, it looks like hope. Even if nothing like us is there to see it. Maybe whatever exists in that future will look up from whatever they have instead of eyes and wonder where their galaxy came from. The same way we do. The Milky Way will die. Eventually, finally, truly. But before that, in the present tense, something unexpected is happening in the data, something that raises the question of whether our galaxy might have one more revival left in it. Because astronomers have recently detected evidence that the Milky Way is receiving new gas, infalling material from the galactic halo. The question is whether it's enough. Whether our galaxy still has something left to give. The Milky Way's halo, the vast, roughly spherical region of diffuse gas, dark matter, and old stars surrounding the galactic disk, contains enormous clouds of hydrogen gas that are measurably moving toward the disk. These are called high-velocity clouds, and some of them are remarkable. The Smith cloud is one of the most studied examples. A massive concentration of hydrogen gas, it contains enough material to form approximately 2 million new stars when it impacts the galactic disk, an event expected to occur in roughly 27 million years. What makes the Smith cloud particularly interesting is the evidence that it was originally ejected from the Milky Way itself, launched by some past energetic event, perhaps connected to one of the AGN episodes we discussed, and now falling back in. The galaxy is recovering its own expelled material. The Magellanic Stream presents an even larger opportunity. The Large and Small Magellanic Clouds, the two satellite galaxies of the Milky Way visible from the southern hemisphere, are being gravitationally disrupted by our galaxy's tidal forces. Gas is being stripped from them and funneled along a stream that connects them to the Milky Way's disk. Estimates suggest this process could deliver billions of solar masses of gas to the Milky Way over the coming billions of years, a substantial external fuel supply. At the galactic center, near Sagittarius A* itself, recent observations have found unexpected pockets of star formation. The Arches cluster and the Quintuplet cluster are extraordinarily young, only a few million years old, forming in what should be an almost impossibly hostile environment, saturated with radiation from the black hole and from the dense concentration of older stars. Life, in a sense, finding a way in the least welcoming neighborhood in the galaxy. The Sagittarius dwarf absorption is also an ongoing enrichment event. As that galaxy continues to be dismembered and pulled into the Milky Way, it is contributing both stellar mass and gas to our galaxy's reserves. The predation continues, and it continues to feed the predator. There's a concept called the galactic fountain that ties all of this together. Gas blown out of the disk by supernovae in the past AGN events doesn't necessarily escape the galaxy entirely. It rises into the halo, cools, and falls back down over timescales of hundreds of millions of years. The Milky Way may be functioning as a kind of thermodynamic recycling system, repeatedly losing and recovering its own material, sustaining itself longer than a simple accounting of gas reserves would suggest. I want to be careful here, because I don't want to give you false hope or false despair. The honest state of the science is that the data is genuinely mixed. Some interpretations of the observations point toward clear long-term decline with no reversal in sight. Others emphasize the incoming gas from the Magellanic Stream and the high-velocity clouds as meaningful recovery, potentially sustaining current star formation rates for longer than previous models predicted. The answer is that we don't know with certainty yet. And I find that more interesting than a tidy conclusion would be. What we can say is that by the most optimistic current estimates, the Milky Way has perhaps hundreds of millions to a low billions of years of meaningful star formation remaining before the decline becomes truly terminal. On a human scale, that is effectively forever. It is irrelevant to anything we or our descendants will experience in any foreseeable future. But it reframes the galaxy's position, not in its final hours, but in what might be its long afternoon, past its peak, declining but not yet finished, still capable of producing new stars, new systems, possibly new worlds with the conditions for life. The ghost still has some warmth in it. Which brings us back to the question the title has been holding. Are we living in a ghost? And is a ghost without value? The revelation that we live inside a dying galaxy is not an argument for despair. It is a recontextualization of our origins, of our rarity, of our relationship to time, and of what we owe to the improbable chain of events that produced us. We are the universe's most complex product to date, as far as we are able to determine. If the Milky Way's death cycle was the necessary precondition for the chemical environment that made us possible, then we are not accidents in a living galaxy. We are the intended outcome, in the physical sense, not the theological one, of a 13 billion-year process of death converting into complexity. The galaxy wasn't trying to make us. But it made us anyway, because that is what death at galactic scale eventually produces when the conditions are right. Our rarity, when you sit with it, is staggering. Consider what had to be true simultaneously. Our solar system had to form in the galactic habitable zone, at the right distance from the center. It had to form at a moment in galactic history when metallicity was high enough for rocky planets to be possible. The Milky Way had to have already gone through enough death cycles to enrich the interstellar medium with heavy elements. The region of the galaxy where a cloud of gas condensed had to have been neither too close to the AGN events that sterilized the inner galaxy, nor too far from the enriching death cycles of the galactic disk. The Sun had to be the right mass to provide stable energy output across billions of years. Earth had to form at the right distance, with the right chemistry, with the right protective neighbors. Any one of those conditions failing, and we are not here. All of them were satisfied, in the right order, by the specific history of a galaxy that has been dying for billions of years. Each condition traces back to the death cycle. Human civilizations have existed for approximately 10,000 years. Written history spans roughly 5,000. Our scientific understanding of any of this is perhaps 400 years old, in its most primitive form, and perhaps 100 years old in a form that would be recognizable as modern cosmology. And we are having this conversation at a moment when the Milky Way still has meaningful activity remaining, when the galaxy still forms stars, still contains habitable zones, still generates the conditions that make worlds like ours possible. We are not at the end of the Milky Way's story. We are somewhere in the long, complicated middle, past the dramatic opening acts, before the quiet final chapters. And the fact that we are here at this particular moment, capable of asking these questions, is itself part of what makes this specific moment in cosmic history unusual. I don't know what to do with all of this, honestly. I started researching this video thinking it would be a story about cosmic death, depressing, maybe a little nihilistic. Something to unsettle you in an interesting way. And it turned out to be the opposite. It turned out to be a story about how death and life are the same process at large enough scales. About how the galaxy that is dying is also the galaxy that made everything alive. I find that hard to hold in my mind all at once. And I think that's okay. Some true things resist being fully held. At the start of this documentary, I told you that you are living inside a ghost. I meant that literally, and I still do. The Milky Way died once, and it is dying still. But a ghost is not nothing. A ghost is what remains when something profound has passed through a place. And what passed through this galaxy, across 13.6 billion years, left behind you. Left behind this moment. Left behind every question you have ever had about the sky, every piece of wonder that has ever moved through you when you looked up on a clear night and felt the scale of it pressing down. That is not a small thing for a ghost to leave behind. But there's one more question. One I've been holding back through all of this. Because if the Milky Way died once and experienced something like a revival, could that pattern exist elsewhere? Could there be galaxies scattered across the universe that have died, partially recovered, died again, across the entire span of cosmic history? Multiple cycles of quenching and revival, each one producing different conditions, different possibilities. And if so, how many times has the death cycle reached the level of complexity that produces something looking up and wondering? How many times has something like us sat under a ghost sky and asked these same questions, in whatever form those questions take for minds shaped by entirely different galactic histories? We'll start answering that next time. In this space documentary, we stepped into the ghost of the Milky Way, we traced its violent birth, its catastrophic slowdown, the black hole that nearly silenced it, the galaxy it consumed, and the impossible chain of deaths that produced every atom of life on Earth. We didn't find a dead galaxy. We found something stranger, a galaxy that died into us. And that changes everything we thought we knew about where we come from. If you made it to the end of this one, this took a long time to put together, and it means everything to know someone watched it all the way through. If it changed even one thing about how you see that sky tonight, share it with someone who looks up. And subscribe, because the next one goes somewhere I think you'll find difficult to sleep after. Next time, we're leaving the Milky Way entirely, looking at the galaxies that are already completely, finally, permanently dead. They stopped forming stars billions of years ago and are now vast graveyards of cooling embers drifting apart in the dark. They're called red and dead galaxies. Some of them are identical to what the Milky Way will become. We'll look at our future. I'll see you there. Also, look up tonight if you can. Even knowing all of this. Especially knowing all of this.